The subjectivity inherent in unsupervised machine learning model selection is a pressing concern, as exemplified by the Hidden Markov Model. This variability and inconsistency are observed not only in human decision-making but also in large language models, LLMs, particularly when different criteria and metrics yield conflicting results. The study underscores the necessity for a more standardized documentation of subjective choices made during model selection processes. It emphasizes the importance of an objective approach to ensure the repeatability and reproducibility of results, which is crucial for scientific research and the robustness of real-world models. The Baum-Welch algorithm is employed to train hidden Markov models, HMMs, where the number of hidden states is unknown and must be determined before training. Information criteria, ICs, are commonly used in model selection to calculate for each candidate model. The IC with the minimum value should be selected, emphasizing predictive accuracy or parsimony. Different ICs have different penalty terms, leading to varying model selections. Researchers have compared the performance of various ICs, with mixed results. Some suggest abandoning ICs and using cross-validation instead. Pragmatic guides for practitioners recommend choosing the Akaika Information Criterion, AIC, for underfitting concerns and the Bayesian Information Criterion, BIC, for overfitting concerns. Model selection is a crucial step in unsupervised learning, and human preference often plays a significant role in this process. This table presents a comprehensive summary of various information criteria, ICs, used for model selection, including AIC, AIC3, AICC, AICU, CAIC, BIC, and ABIC. Each IC is described in terms of its penalty term and the aspect of model selection it emphasizes, such as predictive accuracy or parsimony. Table 2 highlights the best models selected by each IC in 3 different scenarios, denoted as Scenario 1, Scenario 2, and Scenario 3. The models are identified by their number of hidden states, ranging from 2 to 20. The table also highlights the best average model, most consistent model, and best worst-case model for each scenario. The researchers created 3 model selection scenarios by training hidden Markov models, HMMs, using publicly available replay files from StarCraft II, a popular online multiplayer real-time strategy game. The datasets consisted of 30, 490, and 2,980 replay files, respectively, and were used to train 19 candidate HMMs with varying numbers of hidden states. The researchers calculated the IC values for each candidate model and selected the best models based on each IC. The researchers then conducted additional cross-validation tests for the selected models, evaluating their negative log likelihood terms using 5-fold and 10-fold cross-validation. The results are reported in Appendix C. The researchers also designed a self-paced survey to measure modelers' preferences and experiences with different ICs, providing insights into the practical application of these criteria. In the results and discussion section, the study delves into the participants' model selection process, revealing intriguing insights into the cognitive biases that influence their decisions. The researchers employed a mixed methods approach, combining both qualitative and quantitative data to garner a comprehensive understanding of the participants' thought processes. The qualitative data, obtained through think-aloud protocols, exposed significant biases in the participants' model selection. Notably, the majority of participants exhibited a strong confirmation bias, selectively seeking out information that supported their initial hypotheses. This bias led to an over-reliance on simplified models, neglecting more complex, yet potentially more accurate, alternatives. Quantitative analysis of the participants' model selection patterns revealed a striking correlation between their confidence in a model's accuracy and the model's actual performance. This correlation suggests that participants were overly confident in their chosen models, often failing to recognize the limitations and uncertainties associated with them. The researchers also explored the role of cognitive load in model selection, discovering that increased cognitive load led to a greater reliance on mental shortcuts, such as the availability heuristic. This phenomenon resulted in participants favoring models that were more easily comprehensible, rather than those that were more accurate. The study's findings have significant implications for the development of decision support systems, highlighting the need to incorporate debiasing strategies and uncertainty visualization techniques to mitigate the effects of cognitive biases. Furthermore, the research underscores the importance of considering the interplay between cognitive load and model selection in the design of such systems. The study's findings, as presented in Figure 1, Table 3, and Figure 2, demonstrate that the choice of information criterion, IC, for model selection varies across different scenarios. The Bayesian information criterion, BIC, is the most frequently chosen in all three scenarios, highlighting its consistency and reliability in model selection. However, there is inconsistency in participants' model selection preferences, which could be attributed to various factors such as personal experience, knowledge level, or individual interpretation of the data. The results from Table 3 indicate that participants prefer BIC over other criteria, such as the ArXiv information criterion, AIC, due to its ability to balance model complexity and goodness of fit. This preference may also reflect a bias towards simpler models, as BIC tends to favor models with fewer parameters. Figure 2 illustrates the variability in model selection across different scenarios, suggesting that the choice of IC can significantly impact the outcome of statistical analyses. This variability underscores the importance of considering multiple criteria when selecting a model, rather than relying solely on one method. These findings have implications for future research, emphasizing the need for more comprehensive guidelines on model selection and the importance of considering multiple information criteria. Furthermore, they highlight the potential benefits of incorporating machine learning techniques into statistical model selection processes to improve accuracy and consistency. The study delves into the consistency of human and large language model, LLM, predictions in a given task, examining whether these models exhibit similar variability as humans. This investigation is crucial for understanding the potential of LLMs to replace humans in various tasks and for enhancing their performance. To achieve this, researchers employed a two-pronged approach. First, they conducted experiments with human participants. Second, they utilized LLMs to make predictions on the same dataset. The results revealed that while both humans and LLMs demonstrate variability in their predictions, the nature of this variability differs significantly between the two. Humans tend to exhibit a more consistent pattern of errors, often related to their cognitive biases and heuristics. On the other hand, LLMs display a different type of inconsistency, which stems from their complex internal workings and the randomness inherent in their algorithms. These findings have significant implications for the development and deployment of LLMs. They suggest that these models should not be viewed as simple substitutes for humans but rather as tools that can complement and augment human capabilities. Furthermore, they highlight the need for a better understanding of the underlying mechanisms driving LLM variability, in order to improve their reliability and trustworthiness. In conclusion, the study provides valuable insights into the comparative consistency of human and LLM predictions, emphasizing the unique strengths and limitations of each. This knowledge can inform strategies for enhancing the accuracy and reliability of LLMs, ultimately leading to more effective human-LLM collaboration and improved task outcomes. The study emphasizes the crucial influence of subjectivity in machine learning model selection, showcasing divergent preferences between human participants and large language models, LLMs. Both groups exhibited varying preferences, underscoring the need for a nuanced understanding of model selection criteria. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have. ArXiv information criterion, AIC, is a widely used model selection method that aims to choose the candidate model expected to have the lowest error in predicting future data from the same process as the training data. AIC estimates the relative Kullback-Leibler divergence of the likelihood function specified by a model from the likelihood function of the unknown true process that generated the data. To address its limitations, various modifications have been proposed, including AIC3, AICC, AICU, and CAIC. Each of these modifications introduces a different penalty term to balance model complexity and data fit. Bayesian information criterion, BIC, is another widely used method, derived from Bayes' theorem, focusing more on parsimony with a heavier penalty weight. Modifications of BIC, such as ABIC, have also been proposed. The results of these information criteria are presented in Figure 3, where the minimum value of each column is highlighted in green, indicating the best model selected. In scenarios 2 and 3, the information theoretic clustering (IC) algorithm demonstrates varying degrees of effectiveness in recovering underlying cluster structures. Scenario 2, characterized by a moderate noise level and 3 clusters, showcases the IC algorithm's adaptability, with an adjusted RAND index (RE) of 0.93, indicating strong agreement between estimated and true cluster assignments. The algorithm's success is attributed to its ability to capture changing noise levels through varying entropy values. Figure 4 illustrates the IC results, featuring estimated cluster assignments and corresponding silhouette plots, which demonstrate cohesion and separation of clusters, with an average silhouette score of 0.85, indicative of well-defined clusters. In contrast, Scenario 3 presents a more challenging setting, with a higher noise level and 5 clusters, resulting in a lower RE of 0.73, indicating less accurate recovery of the true cluster structure. The decreased performance is attributed to the increased noise level, which compromises the algorithm's ability to distinguish between clusters. Figure 5 highlights the difficulties in cluster separation and the presence of noise-induced artifacts, with silhouette plots exhibiting a lower average score of 0.65, indicating less well-defined clusters. These results validate the IC algorithm's ability to adapt to varying noise levels and cluster structures, while also underscoring the need for further improvements in handling high-noise scenarios. The authors acknowledge the limitations of the current approach and identify potential avenues for future work, including the exploration of alternative distance metrics and the incorporation of additional regularization techniques. By leveraging information theoretic measures, such as entropy and mutual information, the IC algorithm effectively captures the underlying structure of the data, building upon the theoretical foundations established earlier. Cross-validation results are presented, showcasing the performance of various models across 3 scenarios. The second column in each table displays the average of the negative log likelihood term across 5 or 10 folds, with lower values indicating higher likelihood. Paired t-tests were conducted to determine whether the negative log likelihood term average of a model is significantly better than that of other models. In Scenario 1, Model 4 exhibits the best average negative log likelihood term, although the results are insignificant when compared to other models using paired t-tests. Model 6 demonstrates the lowest standard deviation, suggesting consistency across the 5 folds. Model 4 also has the best worst-case log likelihood term value. In Scenario 2, Model 4 again exhibits the best average negative log likelihood term, with insignificant results when compared to other models using paired t-tests. Model 4 also has the lowest standard deviation, indicating consistency across the 5 folds. In Scenario 3, Model 14 serves as the baseline, with insignificant results when compared to Models 13 and 20 using paired t-tests. Model 13 has the lowest standard deviation, suggesting consistency across the 5 folds. The standard deviation across the 5 or 10 folds is presented in the 4th column, with lower values indicating more consistent models. The largest log likelihood term value among the 5 folds is displayed as the worst case in the last column, with lower values indicating better performance. In this model selection study, the authors investigate the performance of various neural network architectures on the task of disease diagnosis from medical images. The study is motivated by the need to identify the most suitable model for this task, given the variability in performance across different architectures. The authors consider 6 different neural network architectures, including DenseNet, ResNet, InceptionNet, MobileNet, ShuffleNet, and SqueezeNet. These architectures are chosen based on their popularity and performance in image classification tasks. The authors use a dataset of 10,000 medical images, equally divided into 5 classes, and split into training, validation, and testing sets. The authors employ a Bayesian approach to model selection, using Bayesian neural networks, BNNs, to estimate the posterior distribution over the model parameters. This approach allows for the quantification of uncertainty in the model parameters, which is essential in medical diagnosis where uncertainty can have significant consequences. The authors use the Atom optimizer with a learning rate of 0.001 and a batch size of 32. The models are trained for 100 epochs, and the performance is evaluated using accuracy, precision, recall, F1 score, and area under the receiver operating characteristic curve, AUCROC. The results show that dense net and res net achieve the highest performance, with an accuracy of 93.5% and 92.8%, respectively. The authors also observe that the Bayesian approach provides a more robust estimate of the model uncertainty, which can be crucial in medical diagnosis. The authors also analyze the computational complexity of each architecture, using the number of parameters, floating point operations per second, flops, and memory usage as metrics. The results show that MobileNet and ShuffleNet are the most computationally efficient architectures, while DenseNet and ResNet are the most computationally intensive. The authors conclude that the choice of neural network architecture has a significant impact on the performance of disease diagnosis from medical images. They recommend the use of DenseNet or ResNet for this task, given their high performance and robust uncertainty estimates. However, they also highlight the need for further research on the computational complexity of these architectures, given the limited resources available in many medical settings. The authors present a novel approach to address the problem of oversmoothing in graph neural networks. They propose a new graph neural network architecture, dubbed Graph Attention with Adaptive Receptive Fields, GARF. GARF introduces a dynamic receptive field mechanism, which adaptively adjusts the scope of neighboring nodes considered during message passing. This is achieved through a learnable attention mechanism, which computes attention weights based on the similarity between node features and the current node's features. The attention weights are computed using the following equation: alpha equals softmax, W underscore AH underscore I, W underscore AH underscore J, where W underscore A is a learnable weight matrix, H underscore I and H underscore J are the node features, and softmax is the softmax activation function. The adaptive receptive field mechanism is implemented using a dynamic nearest neighbors (KNN) approach, where K is learned during training. The authors also introduce a novel regularization term, dubbed adaptive receptive field regularization, to encourage the model to focus on relevant nodes and edges. Experimental results on several benchmark datasets demonstrate the effectiveness of GARF in mitigating oversmoothing and improving graph-based learning tasks. The proposed model's architecture is a complex system designed to optimize energy consumption in smart homes. It begins with an input layer that accepts raw data points from various sensors, utilizing a novel preprocessing technique called sensor data normalization (SDN), to standardize the input data for efficient processing. Following the input layer is the feature extraction layer, where the authors employ a combination of convolutional neural networks (CNNs) and recurrent neural networks, RNNs, to extract both spatial and temporal features from the sensor data. This allows for the capture of spatial relationships between different parts of the sensor data and models the temporal dependencies inherent in the data stream. The activity recognition layer then identifies various activities performed by occupants within the smart home using a multi-class classification approach. This layer leverages the extracted features to classify activities into predefined categories such as cooking, cleaning, or watching television. Next, the occupancy estimation layer estimates the number of individuals present in the smart home at any given time, which is crucial for optimizing energy consumption and ensuring user comfort. The authors propose using a probabilistic approach based on the activity recognition results and historical occupancy patterns. Finally, the energy management layer makes decisions about energy consumption based on the recognized activities and estimated occupancy. The authors suggest employing a reinforcement learning framework to optimize energy use over time, taking into account factors such as the current activity, estimated occupancy, and external environmental conditions. Privacy considerations are also addressed, emphasizing the need for secure data handling and processing practices to protect user privacy. A preliminary study conducted in a real-world smart home environment reports promising performance metrics, including high accuracy in activity recognition and significant reductions in energy consumption. The section concludes with a discussion on potential limitations and future work directions. The authors acknowledge the challenges posed by varying user behaviors and the need for continuous learning and adaptation in the system. They also highlight the potential for integrating additional sensors and data sources to further improve the accuracy and efficiency of the system. The research paper discusses the development of a novel deep learning model for image recognition tasks, focusing on improving accuracy and efficiency. The authors utilized two popular datasets, CIFAR10 and ImageNet, for training and testing their model. They employ standard preprocessing techniques, such as normalization and augmentation, to enhance the model's generalization capabilities. The experimental setup includes hyperparameter tuning using a grid search method and the Atom optimizer with a learning rate scheduler to stabilize the training process. The main results show state-of-the-art accuracy on CIFAR10 and competitive results on ImageNet, demonstrating the model's effectiveness. The authors also provide visualizations of feature maps, offering insights into the model's decision-making process and its ability to capture meaningful patterns in images. The page concludes with a discussion on limitations and potential avenues for future research, including the need for robustness against adversarial attacks and the applicability to other computer vision tasks. The mathematical formulation of the proposed algorithm, detailed on page 16, begins with the objective function, a complex combination of terms designed to minimize the error between predicted and actual outcomes. The authors then introduce the Lagrangian dual formulation, transforming the problem into a more tractable form. The iterative process of the algorithm is highlighted, with the dual variables driving the optimization. The section concludes by analyzing the convergence properties, demonstrating stability and efficiency in reaching the optimal solution. The authors emphasize the novel aspects of their approach, particularly in handling the trade-off between model complexity and regularization. The section on page 17 explores the theoretical foundations of the proposed algorithm, rooted in mathematical underpinnings. It begins by discussing manifold learning, emphasizing its relevance to dimensionality reduction in high-dimensional data. The text then delves into the mathematical formulation of the algorithm, utilizing differential geometry and the Ricci flow to optimize the manifold structure. This optimization process converges to a stable manifold, serving as the basis for dimensionality reduction. The algorithm's novelty lies in leveraging manifold learning for efficient dimensionality reduction, distinguishing it from existing methods. The demographic survey section of the paper presents a detailed analysis of the participants involved in the study. It highlights the distribution of age groups, educational backgrounds, and professional experience. The data is collected to ensure a diverse and representative sample for the experiments. The section emphasizes the importance of a balanced demographic in achieving accurate results. It also discusses potential biases and their mitigation strategies. In the realm of deep learning, optimizing model performance is a paramount concern. A novel approach to tackle this challenge is through the application of metalearning, a paradigm that enables a model to adapt to new tasks and datasets with ease. This concept is particularly relevant in the context of deep neural networks, where the complexity of the optimization process can be a significant bottleneck. To address this, researchers have proposed an innovative technique that leverages a secondary network to adapt the parameters of a primary network based on the input data. This secondary network, trained using a metalearning algorithm, learns to learn from the primary network's updates, facilitating rapid adaptation. A critical component of this approach is the meta-learning update rule, which governs the adaptation process. Mathematically, this is represented by the equation d equals alpha, nabla L, theta, where d denotes the parameter update, alpha is the learning rate, and nabla L, theta, is the gradient of the loss function with respect to the model parameters. This update rule enables the secondary network to effectively adapt the primary network's parameters, resulting in improved performance. The computational complexity of this approach is a significant advantage, as it reduces the training time required for the primary network. By leveraging the secondary network's ability to adapt, the primary network can focus on learning the underlying patterns in the data, leading to improved accuracy and efficiency. While this approach shows great promise, the current implementation is not without limitations. The authors acknowledge that the secondary network's ability to adapt is dependent on the quality of the input data, and that further research is needed to address this challenge. Additionally, the authors highlight avenues for future research, including the exploration of alternative metalearning algorithms and the application of this approach to more complex tasks. The paper introduces a novel deep learning architecture for anomaly detection in high-dimensional data, leveraging the strengths of autoencoders and one-class SVMs. This hybrid model is built around a new loss function that integrates both reconstruction error and a modified version of the SVM's decision boundary. This approach allows the model to effectively identify anomalies while preserving the normal data structure. The mathematical formulations are detailed in the paper, providing insight into how the model operates. The experimental setup is also thoroughly explained, demonstrating promising results on benchmark datasets. This research contributes significantly to the field of anomaly detection, offering a powerful tool for identifying outliers in complex datasets. The author's innovative approach combines the autoencoder's ability to learn compact representations of normal data with the one-class SVM's capability to define a decision boundary for anomaly detection. By integrating these two components, the hybrid model can accurately detect anomalies while maintaining the integrity of the normal data. The paper's findings suggest that this novel architecture outperforms existing methods on several benchmark datasets, highlighting its potential in various applications such as fraud detection, network intrusion detection, and quality control. Furthermore, the authors discuss possible future directions, including further refinement of the loss function and exploration of other deep learning techniques. In conclusion, this research presents a significant advancement in anomaly detection, providing a robust and efficient method for identifying outliers in high-dimensional data. The proposed hybrid model offers a promising solution for researchers and practitioners seeking to improve anomaly detection capabilities in their respective fields. In the realm of model selection, a myriad of techniques have been developed to navigate the complexities inherent in choosing an optimal model for a given problem. This includes cross-validation, which involves splitting the dataset into training and testing sets to evaluate the model's performance on unseen data. Cross-validation is particularly useful for avoiding overfitting and assessing the generalizability of the model. However, it can be computationally expensive and may not accurately reflect the performance on future data if the test set does not represent the true distribution of the data. Another method explored is the use of information criteria, such as Akaika's Information Criterion, AIC, and Bayesian Information Criterion, BIC. These metrics quantify the relative quality of a statistical model for a given set of data, allowing for comparison between different models. AIC and BIC are based on the likelihood function of the model and the number of parameters, providing a trade-off between model complexity and goodness of fit. The paper also delves into the realm of resampling methods, including bootstrapping and subsampling. These techniques involve generating multiple versions of the training and testing sets through random sampling with or without replacement, respectively. By evaluating the model's performance across these resampled datasets, researchers can gain insight into its stability and variability. The survey also touches upon the topic of model selection using optimization algorithms, such as grid search and gradient descent, which can be employed to find the optimal combination of hyperparameters for a given model. Lastly, the role of expert judgment in model selection is discussed, highlighting the importance of human intuition and domain knowledge in selecting an appropriate model, particularly when dealing with complex problems where data quality and availability are limited. In the realm of machine learning, generative adversarial networks, GANs, have emerged as a powerful tool for generating realistic data. However, they are vulnerable to backdoor attacks, where an adversary can manipulate the model's output by introducing malicious data into the training set. To address this issue, researchers have proposed a novel framework called DPGAN, which leverages differential privacy, DP, to robustify GANs against such attacks. The proposed method involves applying a differentially private mechanism to the input data before feeding it into the generator network. This is achieved through the addition of Laplace noise to the input data, calibrated to satisfy the DP constraint. The authors demonstrate that this pre-processing step effectively disrupts the backdoor triggers, making it challenging for the attacker to inject poisoned data. Theoretical analysis reveals that the DPGAN framework provides a robustness guarantee against backdoor attacks, with the level of robustness dependent on the privacy budget epsilon. Specifically, the authors show that the expected difference between the generator's output distributions with and without the backdoor is bounded by a factor dependent on epsilon. Experimental results on several benchmark datasets demonstrate the efficacy of DPGAN in mitigating backdoor attacks. The authors evaluate the framework's performance using various metrics, including the attack success rate, generator loss, and visual quality of the generated samples. The results indicate that DPGAN significantly outperforms existing defense mechanisms, achieving a substantial reduction in attack success rate while maintaining acceptable visual quality. An ablation study was conducted to investigate the impact of varying the privacy budget epsilon on the framework's performance. The results suggest that increasing epsilon leads to improved robustness against backdoor attacks, albeit at the cost of decreased visual quality. This trade-off between privacy and visual quality highlights the importance of carefully selecting the privacy budget to achieve the desired balance between security and performance. The DPGAN framework offers a novel and effective approach to robustifying GANs against backdoor attacks, leveraging the principles of differential privacy to provide a provable guarantee of robustness. This page builds upon the previous sections, which introduced the threat model and existing defense mechanisms, providing a comprehensive overview of the proposed method and its potential implications for enhancing the security of GANs. Page 23 delves into the mathematical formulation of the proposed algorithm, detailing the optimization objectives and the iterative process. The objective function is a balanced combination of reconstruction loss and regularization term, crucial for achieving optimal results. The authors emphasize the importance of this balanced approach in achieving optimal results. The iterative process is explained in detail, highlighting the update rules for the model parameters and the weights. Convergence properties are also discussed, emphasizing the stability and efficiency of the algorithm. The section concludes by discussing the computational complexity and its implications for large-scale datasets. Deep neural networks rely heavily on efficient training methods to achieve desirable performance. A novel optimization technique, efficient gradient descent, EGD, addresses this challenge by adaptively adjusting the learning rate in response to the gradient magnitude. This dynamic approach enables faster training without compromising model accuracy. By leveraging adaptive learning rates, EGD reduces the step size when the gradient is large, thereby mitigating oscillations and improving stability. Conversely, it increases the step size when the gradient is small, accelerating convergence. This adaptive strategy is particularly effective in scenarios where the learning rate is difficult to tune, such as in deep networks with complex architectures. The authors provide a comprehensive analysis of EGD's convergence properties, demonstrating its robustness and stability across various network architectures. Experimental evaluations on benchmark datasets corroborate the method's efficacy, showcasing significant reductions in training time without sacrificing model performance. Notably, EGD's adaptive learning rate strategy allows it to generalize well to diverse network architectures and problem domains. This flexibility, combined with its improved training efficiency, makes EGD a promising optimization technique for deep neural networks. Convolutional neural networks, or CNNs, have revolutionized computer vision by automatically detecting features in images and videos. The architecture of CNNs consists of convolutional layers, which apply learnable filters to small regions of the input image, detecting specific features such as edges or textures. These filters are applied across the entire image to create a feature map. Pooling layers then reduce the spatial dimensions of the feature map, decreasing the number of parameters and computations in the network. The training process for CNNs involves optimizing network parameters using backpropagation, with techniques like stochastic gradient descent and dropout employed to prevent overfitting. Large datasets, such as ImageNet and COCO, are essential for training CNNs. Object detection models like YOLO and SSD utilize CNNs to identify and locate objects within images. Segmentation models, such as FCN and UNet, classify each pixel in an image into different categories. In video analysis, CNNs can be adapted for temporal data using 3D convolutional layers, which apply filters across both spatial and temporal dimensions. Recurrent neural networks, or RNNs, model temporal dependencies in video sequences. Despite their success, CNNs face challenges, including high computational requirements and susceptibility to adversarial attacks. Future research directions include developing more efficient architectures and integrating CNNs with other machine learning techniques. The proposed algorithm is rooted in the principles of machine learning and optimization theory, leveraging a loss function that measures the difference between the model's predictions and actual values. This loss function forms the basis of an optimization problem, which aims to find parameters that minimize the loss. Regularization techniques, such as L1 and L2 regularization, are employed to prevent overfitting and improve generalizability by adding a penalty term to the loss function, controlling the magnitude of the model's parameters. The algorithm's core component is the gradient descent optimization method, a first-order optimization algorithm that iteratively updates parameters in the direction of the negative gradient of the loss function until convergence or a stopping criterion is reached. A step-by-step breakdown of the gradient descent process highlights the importance of the learning rate and the number of iterations. Stochastic gradient descent, a variant of the standard gradient descent algorithm, uses a single data point from the training set to compute the gradient at each iteration, significantly reducing computational costs and improving scalability. Hyperparameters, such as the learning rate and the number of hidden layers, require careful tuning for optimal performance. Various methods for hyperparameter tuning are discussed, including grid search, random search, and gradient-based optimization techniques. Evaluation metrics, such as accuracy, precision, recall, and F1 score, provide insights into the model's strengths and weaknesses, allowing researchers to refine the algorithm further. This page provides a comprehensive overview of the proposed algorithm, detailing its mathematical foundations, optimization techniques, and practical considerations. It serves as a valuable resource for researchers seeking to understand the intricacies of the algorithm and its potential applications in various domains. In addressing the problem of mode collapse in generative adversarial networks, GANs, the authors propose a novel approach by incorporating a regularization term, L_reg, into the discriminator's loss function. This term encourages the discriminator to learn a diverse set of features, promoting mode coverage and reducing the likelihood of mode collapse. L_reg is formulated as the difference between the maximum and minimum values of the discriminator's output over a set of generated samples, effectively penalizing the discriminator for assigning high confidence scores to a limited set of modes. An alternative formulation of L_reg involves computing the variance of the discriminator's output, offering improved computational efficiency while maintaining equivalence to the original formulation. Theoretical analysis reveals that the proposed regularization term leads to a tighter bound on the Earth mover's distance between the generated and target distributions, providing a theoretical guarantee for improved mode coverage. Experimental results on several benchmark datasets demonstrate the effectiveness of the proposed approach in mitigating mode collapse and generating diverse samples. The discriminator's output, as illustrated in Figure 3, showcases a significant increase in the diversity of features learned. A quantitative comparison with existing state-of-the-art methods, presented in Table 1, highlights the improved performance of the proposed approach in terms of mode coverage and sample diversity. While the proposed approach is effective, the authors acknowledge its limitations in scenarios where the target distribution exhibits complex, nonlinear structures. Future work should focus on developing more robust and flexible regularization techniques to address these limitations. The training methodology for the neural network involves the use of stochastic gradient descent, SGD, to minimize the loss function, showcasing its efficiency in optimizing model performance. The application of batch normalization is also highlighted, emphasizing its role in standardizing inputs across the network. To prevent overfitting, dropout regularization is employed, significantly impacting model generalizability. Additionally, the incorporation of learning rate schedulers is discussed, which dynamically adjust the learning rate based on training progress. The model's performance is evaluated using metrics such as cross-entropy loss and accuracy. The authors propose an algorithm called Efficient ML, designed to enhance the efficiency and accuracy of a specific machine learning model. It reduces computational resources required for training and testing while maintaining or improving the model's performance. Efficient ML consists of novel approaches to data preprocessing, feature selection, and hyperparameter tuning. The authors detail how each component contributes to the overall efficiency, providing a comprehensive understanding of the underlying mechanisms. The mathematical derivation of efficient ML's core equations is crucial for understanding its functionality and potential applications. The section includes a detailed analysis of time and space complexity, demonstrating significant computational cost reductions compared to existing methods. This is supported by graphs and tables showing efficiency gains under different scenarios. The authors also discuss limitations, assumptions, and potential future work, adding credibility to the research and encouraging further exploration. The authors introduce a novel approach to address mode collapse in generative adversarial networks, GANs, by adding a new regularization term, L_C, to the discriminator's loss function. This term encourages the discriminator to be sensitive to input noise, promoting diversity in generated samples. L_C is mathematically derived as the expectation of the squared difference between the discriminator's output and a target Gaussian distribution with mean zero invariance sigma-2. It consists of two terms, one representing the discriminator's ability to distinguish between real and fake samples, and another penalizing the discriminator for insensitivity to input noise. The authors argue that L_C promotes robustness in the generator, forcing it to produce diverse samples less susceptible to mode collapse. Figure 3 visualizes the improvement in diversity and quality of generated samples using this approach compared to baseline GAN models. The computational complexity analysis shows that the additional cost of L_C is negligible compared to overall GAN training costs. Limitations include the choice of sigma-2, which may affect performance. Future work could involve adaptive selection of sigma-2 during training. In a real-world demonstration of their proposed methodology, the authors apply it to optimize energy consumption in a smart home environment. This smart home system comprises various devices, including heating, ventilation, and air conditioning, HVAC, lighting, and appliances, all controlled by an IoT gateway. To model the complex interactions between these devices, the authors employ a multi-agent system, MAS, framework. Within this framework, each device is represented as an autonomous agent with its own distinct goals, preferences, and constraints. The MAS framework facilitates the negotiation and coordination of energy consumption among devices. The authors formulate an optimization problem to minimize energy consumption while satisfying the device's goals and constraints. This problem is solved using a distributed optimization algorithm, which ensures that the solution is both optimal and decentralized. The case study reveals that the proposed methodology achieves significant energy savings, with a reduction of up to 23% in energy consumption compared to a baseline scenario. The authors also analyze the impact of various factors, such as device scheduling and user behavior, on energy optimization. The results demonstrate the effectiveness of the proposed methodology in reducing energy consumption in smart home environments. The authors also discuss the limitations of their approach, including the assumption of perfect communication between devices and the need for further research on integrating human behavior into the optimization framework. Future work includes exploring the application of this methodology to larger-scale smart grids and incorporating additional factors, such as renewable energy sources and energy storage systems. Demographics data, as discussed in the section on demographics, is crucial for understanding gender distribution within a dataset. Ensuring a balanced representation of males and females is essential to prevent biased results. The correlations section delves into the relationships between various variables, highlighting their significance in the analysis. Figure 6, which focuses on gender distribution, illustrates the proportion of male and female participants in the study. This information is vital for comprehending how demographic factors influence the outcomes and for ensuring that the results are generalizable to the broader population. Researcher-specific factors, such as risk attitude and machine learning experience, exhibit individual consistency, influencing the approach to model selection. To demonstrate this, example prompts are provided for large language models, specifically highlighting hidden Markov models. The selection of these models is based on various information criteria, including ArXiv Information Criterion, AIC, AIC3, AICC, AICU, Consistent ArXiv Information Criterion, CAIC, Bayesian Information Criterion, BIC, and Adaptive Bayesian Information Criterion, ABIC. Each criterion is applied to identify the optimal model, resulting in a range of selected models with varying numbers of hidden states, from 2 to 20. This diversity in model selection underscores the complexity of the dataset and the researcher's nuanced approach to model evaluation. By considering multiple information criteria, the study highlights the importance of robust model selection in accurately capturing the underlying patterns in the data. Cross-validation tests revealed distinct results for different metrics in evaluating the models. The model with 2 hidden states excelled in the best average metric, showcasing optimal overall performance. In contrast, the model with 6 hidden states demonstrated stability across folds, earning it the title of most consistent model. Meanwhile, the best worst case metric favored the model with 4 hidden states, indicating its resilience against adverse scenarios. These disparate results underscore the multifaceted nature of model selection. While the best average metric suggests the 2 hidden state model as the top choice for overall performance, the most consistent and best worst case metrics highlight the 6 hidden state and 4 hidden state models, respectively, for their consistency and resilience. Ultimately, the selection of the best model hinges on the primary consideration, whether it's overall performance, consistency, or resilience against worst-case scenarios.